Hello everyone. Today we're going to look at the work energy theorem. Up to this point we've talked about work and power. Yesterday we talked about the different types of energy, specifically kinetic, gravitational potential, and elastic potential. Today we're going to look at the connection between work and those kinds of energy. So first bullet point, the work done on an object changes the amount of energy that object has. Okay, so when work is done on an object, the amount of energy is going to change. If a positive amount of work is done, that means energy has been added to the object. And vice versa, negative work removes energy. So we get this equation, this relationship that the work done equals the change in energy of an object. So in other words, work equals the change in kinetic energy of an object, or it could be that work equals the change in gravitational potential energy of the object, or the work could equal the change in elastic potential energy of the object. It depends what's happening. Is the object changing speed? Is the object changing height? Or is the object compressing or stretching a spring? Okay. And change in science class always means final minus initial. So in other words, this could be 1/2 mv final squared minus 1/2 mv initial squared. That would be the change in kinetic energy, final minus initial. Or the other way that you could write this, since these two terms share 1/2 m, you could just write it as 1/2 m parentheses v final squared minus v initial squared. That's kind of a simpler way to write it. Now sometimes your initial velocity will be 0, and so you can just do 1/2 mv final squared and be done. Similarly, change in gravitational energy would be mgh final minus mgh initial. Again, final minus initial, or in other words, mg delta h. So change in height. And lastly, change in elastic potential energy, 1/2 k x final squared minus 1/2 k x initial squared, which similarly can simplify to 1/2 k f squared minus f squared. And it's worth noting that this initial stretch is usually 0. Usually the spring is not stretched before the problem starts. So it's almost always 0. Let's move on to the first example. Playing shuffleboard, a 0.25 kilogram puck is pushed with 6 newtons of force for 0.5 meters, starting from rest. Assume no friction. We want to know in part A, how fast will the puck be sliding after it's been pushed for 0.5 meters. So we're doing work on the puck. We're pushing it, causing it to move, and that's going to cause the puck to go from rest to not being at rest. So it's causing it to gain kinetic energy. So the work we do changes the kinetic energy of the puck. And we know that work is force times displacement times cosine of theta, but we don't need to worry about that here. No specific angle. That equals 1/2 m v final squared minus v initial squared. It says the force is 6 newtons, the displacement is 0.5 meters, the mass is 0.25 kilograms, final velocity we don't know, and it started from rest. Do a little algebra. The final velocity of the puck is 4.9 meters per second. Part B, how much work would it take to stop the puck? So again, the work that's going to be done to stop the puck is going to equal the change in kinetic energy of the puck again, except now we're trying to stop the puck, so you can expect it to be a negative amount of work. So work equals 1/2 mv final squared minus v initial squared. 1/2 0.25 0 squared minus 4.9 squared. Calculate it out. The work you should do is -3 joules. Again, this answer should make sense that it's a negative amount so that the energy is being removed and the puck comes to a stop. Let's move on to our next example. A string is stretched 50 centimeters from equilibrium as shown in the graph. We've got a force displacement graph. What is the spring constant of this spring? So first of all, you need to understand that the spring constant on one of these graphs is the slope. So rise over run, if we pick a 0, 0, and then 0.5 comma 50, the slope would be rising 50 newtons over the course of 0.5 meters, which gives you a spring constant of 100 newtons per meter. That's our K value. Part B, how much work does it take to stretch the spring 50 centimeters? So in this case, the work that we're doing is going to change the amount of elastic potential energy stored in the spring. So work equals 1/2 K x final squared minus x initial squared. 1/2 times 100. Final stretched distance is 50 centimeters, which is 0.5 meters. Squared minus 0 squared because the spring was not stretched initially. This equals 12.5 joules. It's worth noting that this 12.5 joules would also be the area underneath our graph from 0 to 50. So if I were shading in the area from 0 to 50 centimeters or 0 to 0.5 meters, this area here would represent the energy stored in the spring or the work done in stretching the spring, 50 centimeters. Part C, one Snickers bar contains 250 calories with a capital C. One bar contains enough energy to stretch the spring 50 centimeters. How many times? So first of all, you have 215 calories with a capital C. That's 215,000 lowercase calories. So interesting side note, when you read the wrapper on food items, when it's spelled capital C calories, they're talking about kilocalories, thousands of calories. And each calorie is the equivalent of 4.184 joules. So if we do a little quick conversion here, 1 calorie, 4.184 joules, you get 899,560 joules contained in one candy bar, or one Snickers. And so in part B, we figured out that it takes 12.5 joules of energy to stretch this spring one time. So to find out how many times you could stretch this spring using the energy stored in one Snickers bar, we just take the energy, 899,560 joules divided by 12.5 joules per stretch. Find out that it would do almost 72,000 stretches, 71,965 stretches. Lots of energy in those candy bars. Last but not least, we've got a 5 horsepower engine that's used to lift a box via a pulley. In 1 minute, how high can the engine lift a 100 kilogram box? This is our 100 kilogram box down here. We're going to lift it up using this machine, engine. And so the work done by the engine is going to equal the change in gravitational energy of the box. The box is going to get lifted up. That changes its gravitational potential energy. Now we're told that this is a 5 horsepower engine. Remember, horsepower can be converted into watts because every 1 horsepower is 746 watts. So that means our engine can produce 3,730 watts of power. And it says that we're going to use this for 1 minute, and we know power is work over time. So if our power is 3,730 watts, and we're using it for 60 seconds, that means the amount of work that our engine is going to do is 223,800 joules worth of work. So 223,800 equals mg change in height. Mass of our box is 100 kilograms. We're on Earth. 9.8 is g. Final height we don't know. Initial height is 0. A little algebra. And your final height is approximately 228 meters above the ground. Okay, this is assuming our reference point is the ground at 0